So as we finish up the semester, we're going to kind of talk a little bit about how you take a lot of the knowledge which you've gained so far. Um, we kind of talk about this as kind of like building a toolbox of reactions. Depending on what task you need, you might need a screwdriver or a hammer or a saw. All of those different tools are going to be different reactions for you. And we're going to build out a huge toolbox for you to be able to kind of make whatever you want in terms of molecules. So we've learned about bromination, we've learned about nucleophilic substitution, we've learned about elimination reactions, and we've now just kind of finished up a lot of our talk on electrophilic addition. Orgo 2 is going to focus on continuing to add more and more different types of tools to that toolbox. But the actual using of those tools, how do you actually build an ideal synthesis, is where, at least from my own sake, where I really kind of fell in love with organic chemistry. How can you take all of these interesting and unique types of reactions and then use those to create a cool and interesting molecule? For my own research, I use that to make materials that are conjugated polymers that can conduct electricity and be used in solar panels. You have a lot of organic chemists who do a bunch of medicinal or drug discovery, trying to determine or design new types of drugs that can cure cancer, Alzheimer's, all kinds of medical issues. The possibilities are truly endless, and the actual designing of syntheses to a specific a specific product is where I think organic chemistry gets super cool. So one of our kind of questions or our broad themes that we kind of want to think about as we kind of close out the semester is, what is, an ideal synthesis? We've done a bunch of different reactions, and we've even saw in that last chapter, there's a bunch of different ways we can add pretty similar groups. We saw multiple different reactions where we can add an alcohol or add a bromine. So how do we choose which one we would want to use in a specific case? And there are some kind of big considerations which you'll generally think of as you're actually doing chemistry for an ideal synthesis. So ultimately, you're going to want your reactions to be highly efficient. Highly efficient means that they have really high reaction yields. They don't have to have a bunch of steps, including workups. You want it to be robust. You want to be able to scale it up. You want to be able to work on a variety of substrates. So that's your kind of like R-leaving group, if you will. If it only works on just a bromine and doesn't work on a chlorine, that's not nearly as good. And it needs to be reproducible. So if I do it, you should be able to also be able to do it. We want chemistries that are going to be safe. We don't want chemistries that are going to have a lot of toxicity. A common example in my lab are a lot of pyrophoric reagents like butyl lithium compounds. There's also an economic or a cost associated with your materials. You want cheap materials ultimately. And we mentioned that a little bit even just in the last chapter, where we compare osmium, which is incredibly expensive, compared to permanganate, which is significantly cheaper. But there are also pros and cons to those where you need to kind of balance. And then finally, we want it to be environmentally friendly. We don't want to be generating a lot of waste or toxic intermediates. We want to have high atom economy. So we don't want to be using a bunch of molecules that aren't going to be adding to our specific substrate. And these are some kind of like big, broad things that you'll kind of eventually start to think about as you learn more and more organic chemistry throughout your career. So the ultimate goal of organic synthesis is to do organic chemistry, to design an organic compound, which we'll often call a target molecule. And we want to make these from things that are readily available, things that exist in our own laboratories. Now, one of the things that we're going to talk about as an introduction here, and then talk about a ton more in Organic 2, is going to be this idea of retrosynthetic analysis. And that's going to be kind of the process of designing a strategic plan, a strategy which is going to describe how you're going to take a readily available starting material and convert that into your final target compound. And to that, there are kind of two key concepts that are going to, or two keys that are going to fit into that. The first is going to be knowledge about reactivity. And that was one of our main focuses of Organic Chemistry 1. Can you identify a nucleophile and an electrophile? Can you think about the movement of electrons? Can you think about how these molecules sit in space in their 3D structure and how that can affect their reactivity? that was one of our kind of big core focuses that we really wanted you to capture. The next then is thinking about the designability, which we're going to be starting to introduce now, and we're going to see that heavily in organic chemistry too. And that's how do you put multiple reactions together in order to build a specific target. So there are going to be two types of new terms that we're going to introduce here. The first is that retrosynthetic analysis. And retrosynthetic analysis, or retro for short, is a problem-solving technique which is going to be thinks about ways in which you can do a transform on a molecule. And what retrosynthetic analysis does is it starts with your final product and then works backwards to simpler and simpler and simpler. And you kind of build out this tree. And there's actually a graphic that I'll show that is literally a tree when we start talking about that in more detail. So retrosynthetic analysis is kind of like the opposite of what you'll do in the lab, like physically. Retrosynthetic analysis is all the design or the planning. Thinking about, here's your final product, how are you going to get there? The opposite direction of what you would actually physically do, starting with starting materials, and then do a reaction, do a reaction, do a reaction. That is multi-step synthesis, where you then kind of use the tactics to actually follow along that forward direction. Now, retro can either be really, really cool for people or really, really frightening for people, depending on kind of like your right brain, left brain kind of thought process. Retro can be very artistic and left-brained, and even with that, I kind of have this kind of question here. Is there a standard strategy to how do you look at a target and think about how you break it down? And not really. I mean, we'll talk about a few strategies, but like there's not a standard strategy that works for every single one. There's a bunch of freedom and imagination and even risks that's associated with words associated with this idea of synthesis. It is not only like super scientific, but it is also super artistic. And there's often a lot of beauty and elegance which you can design through chemistry. So when we talk about this idea of a tree, this is actually a graphic from the Nobel Prize Committee in 1990 for E.J. Corey's Nobel Prize in Chemistry, which is focused on multi-step and retrosynthetic analysis. So the idea of the retrosynthetic analysis is kind of like this tree where you see here. Way at the bottom, you have a target molecule, and this is a specific molecule that you want to make. And what we're going to do is we're going to think backwards. So we're going to kind of, as that tree grows, go to simpler and simpler and simpler starting materials all the way till we get to some individual starting materials that we will do transformations on. Once we've identified a bunch of our starting materials, we're then going to kind of go in the opposite direction. So you have multiple starting materials. Those are going to combine and combine and combine and combine and transform until you eventually get to your target molecule. Now, I'm going to show a slightly obnoxious example here just to kind of show some transformations. When we think about the big considerations of things being robust, environmentally friendly, economically accessible, safe, and highly efficient, this synthetic path fails on a lot of them. But I wanted just to show like a variety of kind of transformations here. Now, there are going to be two types of synthetic routes, and we're going to talk about these in Orgo 2, and that's going to be linear versus convergent synthesis. Here, this is a purely linear synthesis, so I start with one starting material, and I just keep pushing it all the way, just transform it, transform it, transform it. Convergent synthesis is actually what you see a little bit more on that tree, where you have multiple different materials that kind of come together. The reason we haven't really talked about it at all in Orgo 1 is we haven't really learned any like carbon-carbon bond forming reactions, which we're going to talk about a ton in Orgo 2. So just to kind of show an example of what a retrosynthetic analysis looks like and how we kind of think about retro, let's go ahead and start with a slightly complicated starting material. I have the name there. It has some chirality. It's a 1, 2, 3, 4, 5-membered carbon system. It has 2 aldehydes and 2 alcohols. And that's a molecule that we can't just go on to a chemical vendor like Fisher or Sigma Aldrich and buy it super easily. So we would need to make it. So one of the ways that we'll think about how do we make it is think about what reactions do we know that would be able to kind of go in the opposite direction to get our product. So to kind of provide an example here I see that I have two aldehydes, which I've shown in blue. And I know, for example, if I have a double bond and I cleave a double bond through a ozonolysis reaction, that can make two aldehydes, for example. That's if I use my O3. If I use my stronger conditions like permanganate, it would make two carboxylic acids. So if I'm thinking of in the opposite direction, I could think about combining those two blue groups into make a double bond and then have a 5-membered ring here with my two alcohols with my defined stereochemistry. And if I take this material that I have down at the bottom and undergo ozonolysis, and that would be with your conditions with, so in your forward reaction here, that would be your ozone and other components. But we're thinking in the opposite direction. So we're gonna just break it down. So I see like, oh, two aldehydes, that's a common product in ozonolysis. So if I do an kind of like reverse reaction, what would be my starting material that would be required to give me my product? And this is where like that good knowledge of all the different reactions which we're learning is going to pay dividends. So then if I look at my next reaction or my next planning of my retrosynthetic step, here I see I have a diol, so I have two alcohols, and they have opposite stereochemistry. And I think back to chapter 8, and I think about all the different ways to add diols. I have things like the osmium, but that would give me syn addition, where it'd be wedge or dash. Here I have opposite. And I know that one of the ways I can do that is through a kind of backside attack, which is going to be the opening of an epoxide. So I can think, oh, if I turn those two alcohols into an epoxide, and that's a transform. So that's not a reaction, because it's going the opposite direction. So we call it a transform rather than a reaction. That transform would give me an epoxide. And then in the forward reaction, from that epoxide to the diol, I can say I'm going to use acid and water, and that is going to do my acid catalyzed hydrolysis or ring opening of that epoxide. And that's where we're going to be kind of thinking in that opposite direction. Same thing, I now have an epoxide, and I think about what are ways which I can make an epoxide. I can make an epoxide from a halohydrin. Now, there is a bunch of creativity and differences you can do. There's not going to be one right answer. For example, in my halohydrin, what if I, instead of drew this molecule, what if I drew the opposite, where I drew it with a bromine here and an OH there, where I switch, where I add my Br and my OH. Both of those, if you expose to in the forward reaction, if you expose to a base, you deprotonate your alcohol, it would attack the electrophilic carbon attached to the bromine leaves, you get an epoxide. Both of those would form. So both of those are perfectly fine routes. And where there'll be some kind of trial and error is one of those might be a lot easier to make than the other. There are also some considerations that you'll eventually need to take into account when you go in the forward reaction. So for example, when I think of my acid catalyzed ring opening of the epoxide, that does form an anti-configuration. However, that will actually form the enantiomer as well, which would be the OH and the OH. And both of those will form. So if I wanted to get the specific chirality associated with the one that I've drawn here to give me my product, I would have to go through and I'd have to separate out or remove any of the byproduct that formed with the opposite stereochemistry. So even though in a retrosynthetic analysis, you can kind of propose a possible starting material, that doesn't necessarily mean that's going to be the best one. And when you actually do the chemistry in the forward reaction, there will be some troubleshooting or kind of figuring out, oh, maybe that's not the ideal synthesis. What are some other things that we can do? Kind of continuing on this route, if I look at the product, which is my halohydrin, I see that there's still a double bond. And I know I can get double bonds through eliminations. So I maybe considering, how do I put that bromine there, and say, oh, what if I do a halogenation of a double bond? So if I was going to do that, I could put a bromine and a hydrogen on, and I can eliminate. Now, of course, this can also have multiple different eliminations. It's not going to eliminate just to form this product. There's a few other byproducts which can happen. That's one of the reasons why this isn't the perfect example, but it's trying to give you a bunch of different reactions that we've kind of done. But I can do an elimination. That can be an E1 or an E2. There's no, well, there are pros and cons. When we think about things like rearrangement, think about major products that can form from each. You might prefer doing an E2 over an E1, for example. Here I see that I have in my orange and my pink 2 bromines, and those bromines can be made from a double bond. So if I have a double bond, I can toss in Br2 in the forward reaction and add 2 bromines. Those are going to have opposite stereochemistry, so one would be a wedge, one would be a dash, but we don't have any defined, so that's okay. I also see I have an alcohol, so I can actually make an alcohol from a double bond. That's going to be a hydration reaction, so that's going to be taking a double bond, adding your acid and water in order to do your Markovnikov hydration reaction. Similarly, like if I'm thinking about getting a double bond, I can go through an elimination, and I can kind of think about all kinds of different ways where I eventually get down to a very easily starting molecule, cyclopentene. To be honest, actually, this one right here would also probably be perfectly fine, this cyclopentadiene. But a much simpler starting material that I can then do a bunch of forward reactions. So kind of in summary, the core idea of retro is kind of thinking in the opposite direction. Think about, if I have a specific product, are there specific parts of it, are there specific functional groups, for example, that I know how to add? And then if I know how to add those, what is going to be that reaction, and then what must be the starting material? And you kind of just keep working backwards and backwards and backwards until you get to something that's going to be a nice starting material. For the examples that we're going to do in class, I'm actually going to give you a starting material and the product, so you kind of have a little bit of like help trying to figure out what you're trying to go back to. But in reality, what you're trying to go back to can be whatever you have in your lab. So like when I'm planning a reaction for my own research group, a lot of times I'm focusing on, if I'm trying to make a specific target, I have specific chemicals in my lab. How can I use those as starting materials to get to that product? And that's this core idea of doing retrosynthetic analysis. So we're thinking backwards, and we're designing kind of our ideal reactions to try to figure out, how do we make what we want to make?